Let's take a look at another situation. We're going to look at comparing two third grade classrooms where one classroom ended up receiving a intervention special reading program and the other one maintained their current stuff. And so we're going to look at the one classroom that had the extra treatment compared to the other classroom. Now, our classroom that received the treatment had 21 students. Our classroom that did not had 23. Here's the mean reading scores after the 8 weeks, and here's the standard deviations of each group. Now, when you're looking at your degrees of freedom, you want to look at the smaller sample size, which is 21, and subtract 1. So our degrees of freedom from a conservative point of view is 20. And that's what you want to look for if you're dealing with your table C in the back of the book. However, if you're doing it by technology, you don't want to be real concerned about that. Looking at table C, we were 20 degrees of freedom, so you go across on your 20 row here, right here, and we are looking at 95% confidence interval, and so you would find the intersection of those, and that would be right here. And so that's your T star that you would end up using. And so we have that recorded over here for us. Now, once again, your confidence interval is the difference in your two means plus or minus your margin of error. Remember, your margin of error, once again, is that T star that we just figured out right here, the 2.086, times your standard error. Your standard deviation is your first group squared over your sample size, and that's given to you in your chart up here, plus your standard or margin standard deviation squared over your sample size of your other group underneath your square root. So what we're going to do to figure out our confidence interval by hand is we're going to subtract the two means. In this case, we're taking our treatment group minus your control group because we're trying to see if there was a difference, a positive difference by the treatment. So you take your 51.48 minus your 41.52. That's where this 9.96 comes from. Then you go plus or minus your margin of error, and that's what we had figured out right here, which is 8.99. So it's the difference in the two means plus or minus your margin of error. It could be given to you that way. If you go ahead and take your difference in your means and subtract your margin of error, that's where the 1 comes from. Or if you take this and you add your margin of error, that's where the 18.9 comes from. We could go ahead and use our calculator to do this too. Once again, to do that, you're going to go to the stat, over to test, down to your two sample T interval, and then you're going to go ahead and enter your data. Enter your data from your chart, letting these ones be your treatment group, letting the twos here be your control group. Set your confidence level to 95 because that's what we're looking for here. Remember, you never want to pool, and then you go ahead and you calculate. And so then, instead of getting our confidence interval to be from 1.0 to 18.9, we get a better estimate here from our calculator because have a more accurate degrees of freedom. We'll be talking about our degrees of freedom formula later. So it's really 1.23 to an 18.68 for our true difference in the two means for our 95% confidence interval. Now, how robust is the T procedures? Well, for the most part, they're fairly robust. They work great if the sample sizes are equal and the distributions are the same. However, even if there's small variations from that, they still work fairly well. It's important that you have a simple random sample from each group, and it'd be nice if the sample sizes were normal, but even if they're close to being the same, distribution will be okay. Now, if your sample sizes add together to be less than 15, your samples need to be close to normal and no skewedness or outliers. If you do have skewedness or outliers, you don't want to use the T. However, if your sample sizes are adding together to be more than 15, if they have no strong outliers or strong skewness, then you can go ahead and use your T procedures. Now, if you have large sample sizes, you can even use your T procedures when you have strong skewed distribution. Now, when we're talking large, we're talking 2 sample sizes that add together to give you 40. Well, for the most part, that's really not that hard to reach. So your 2 sample T procedures are fairly robust, but consider the situation though when you're dealing with really small samples, and they got to be pretty much the same distribution. Now, conservatively again, for your degrees of freedom, we use the smaller the 2 samples, and we go and subtract 1. Now, your calculator uses this formula right here. This formula would be a challenge to do by hand. You can do it by hand. I wouldn't recommend it. But your calculator or any computer program you're going to use is going to use this formula. You'll enter all the information. It's going to plug it into the formula, and it's going to give you much more accurate degrees of freedom. So if you're using any technology, it's going to give you much more accurate degrees of freedom and more accurate p-value if you're doing a test, or confidence interval if you are doing that. However, if you're doing it by hand, if it says conservative, you use this for your degrees of freedom. If you're asked to find the degrees of freedom and it says use software or computer program, use your calculator. Now, here's what you would get doing it by hand to figure out your margin of error using Table C. If you're using Excel, it would still go ahead and give you your degrees of freedom and your T statistic, or if you're using other programs available like SPSS, it would still do the same thing. Once again, you never want to pool when you're doing your t-test, 2-sample t-test, or your 2-sample t-interval. Now, when we're looking at these situations, we want to see if they're a 1-sample test, match pairs, or if they're 2 totally separate samples. So here we're looking at the vitamin content of bread immediately after baking versus 3 days later. Notice it's the same loaves you're comparing, so therefore it would be a match pair, a before and after situation. Here you're looking at the same type of thing. However, you're dealing with 2 totally separate groups of bread, so it's a 2-sample t-test. So is this a 1-sample, a matched pair, or a 2-sample? In this case, it's a 2-sample because you're looking at 2 totally different groups of women. So what about these last 2? So here you're looking at houses that have a fire extinguisher and houses that don't, 2 totally different groups, so it's a 2-sample situation. Over here, you're looking at the 2005 vehicles, and you want to know if the average is, for these newer vehicles, is higher or lower. Well, it's really just a 1 sample because you're looking at the sample from the 2005 and you're comparing it to previous known data. You can also do a comparison of the standard deviations from your 2 samples. That's referred to as your F statistic, but it's really not a robust situation, so we never want to do that ourselves. We'll leave that to the professionals, so hence you never want to do a F statistic. So let's go ahead and take a look at these here. So pause it while you read through these and then answer the question. In this case, we're dealing with a matched pair because you're dealing with the same group of students and you're basically giving them a pre-test and a post-test comparing their differences. So here we're looking at our national parks. And what is this one? In this case, it is two independent samples because it's two different national parks. So here, what is the basically null hypothesis? Well, when we're looking at this here, we're always assuming that there is no difference between the two means. And in this case here, we're trying to see if there's a difference in the GPAs. So it's going to be A. Now, it is possible you said B, and that would be okay too. When there is no differences in the means, you're assuming that the means are equal. And when there's no differences in the means, and you're trying to see if there's a difference, it means the two means are not equal. So if you put down A, that's great. If you put down D, that's also acceptable. So if our p-value is between a zero point 0.2 and a 0.25 and your significance level is at 5%, what are you going to conclude here? Well, since your p-value is larger than your significance level, you are going to fail to reject your null hypothesis, and you're going to say there is insufficient evidence to say that there is a difference in the GPAs. So here you're given a 95% confidence interval for the difference in the two population means. Which one of these would be correct? We would then say we are 95% confidence that the mean of the difference between the GPAs is this interval. We are wondering for this situation if it's a matched pair or if it's a two sample. If it's a matched pair, why? If it's a two sample, why? In this case, you're comparing elderly patients to younger patients, so it's definitely two different groups. So it's a two sample situation. Their two groups are unrelated to each other. So considering that situation, what are we really going to be studying? Are we going to look at the differences in the elderly and the young? Are we going to divide the elderly and the young? Or are we going to add them together? In this case, it's going to be the differences in the means of the elderly and the young. Now, for this situation here, I like writing it like this, but technically if you did the mu of the differences where you're subtracting the two, that's part A, so that would be okay also. So what would be our hypotheses for that situation? Would it be A, B, C, or D? Well, in this case, we're going to say D. However, oh, never mind, I was going to mess up. Your one null hypothesis is that there is no difference between the elderly and the young, so when you subtract them, you get 0. We're assuming that the elderly are going to have a bigger change than the young, so we're looking for that difference to be greater than 0.